Hi everyone, it's Michaela. I'm going to try and film these videos for you as part of the final SI review series that me and Ethan are trying to hold for you guys. These videos that I'm posting are not going to be the greatest quality. The lighting's going to be not the greatest, and sorry it's on paper, here's my pen. But that's the best I could come up with on really short notice. So hopefully this will help you. I'm going to start with one of the more important mechanisms that need to be emphasized, Fischer esterification. So here we go. So I will move my hand periodically so people can, see what I'm writing clearly without the shadow. But this is the best that I have right now. So, all right. So for Fischer esterification, there's a few things that we need to keep in mind. So the first thing I'm going to do is I'm going to write out the full general mechanism for you all. I'm going to try and use some colors so we can see the different components clearly. And I'm going to try and annotate this reaction for you a little bit more detailed than before, just to help you out. So for Fischer esterification, esterification means we're creating or synthesizing esters, right? So we're going to start, for this we need alcohol, which I'm going to write as ROH, right? The R group could be literally anything, as we know. And we're going to also need carboxylic acid. Okay. And we're going to add strong acid, which I'll denote by H+. H+ means that it's literally any strong acid. So you could have, I'll just put strong acid, but you could have H2SO4 or HCl or something like that. That could do the trick for you. And that's the purpose of having the strong acid is to convert the alcohol into a better leaving group, because we know that usually, not always, but usually alcohol doesn't leave by itself, and OH does not leave by itself, so we need to protonate it somehow, and it comes from that strong acid. And we also need some heat to make the reaction go faster. Okay, and then that'll give you, on this side of the reaction, that'll give you our ester product, right? The R could be anything. And so this is our ester. And it'll also give you water. Okay, so that's the generic reaction. Now, before I move on to the actual mechanism, there's a few things that I want you to know about this. Number one, this reaction is acid catalyzed. That means that you need to use the acid to make it run or to go faster. So a catalyst makes it go faster. It changes the kinetics but not the actual reaction. So that's why you need the acid. And as we'll see at the end of this mechanism, since acid is a catalyst, we're going to have to regenerate it at the end because that's the definition of a catalyst, right? And you also need to know that Fischer esterification is reversible. This means that you can manipulate the reaction to favor either the reactants or the products. So what I mean by that is, if you have excess of, let's start with excess of the alcohol, right? So excess of the alcohol means that you're going to favor the ester formation. Now, if you're confused on how I got to that conclusion, just think of Le Chatelier's principle from Gen Chem, right? So what this means is, if you have a lot of ROH, a lot of the alcohol right here, you're going to basically push the reaction forward, right? So it can relieve the stress on the left side of the equation, and you're going to favor the ester formation. Now, let's say you had excess water, right? You're going to favor the carboxylic acid, right? And that makes sense because if you have a lot of water, which is on this side of the equation, you're going to shift the equilibrium to that side of the equation, right, to the left, and you're going to make more of the carboxylic acid. Okay, so that's what I mean by reversible, and you can manipulate to favor either side. Okay, so that's a very important principle about Fischer esterification. Great, so now we'll actually start the reaction. So we're going to start actually by, we're not even going to use the alcohol in the beginning. We're going to actually start with just the carboxylic acid. So I'm going to use this simple carboxylic acid, so with a methyl group on the other side is the R group. Okay. And the first part is we need to make it a better electrophile. Okay. So we're going to have, let me use the black. We're going to have H2SO4, and yes, you need to know the structure of this. Okay, so here it is. And it's got, of course, this acidic hydrogen. So the lone pairs on this carbonyl oxygen are going to grab that H, donate those electrons back to that oxygen. So the first step is carbonyl oxygen grabs H off the strong acid, which in this case, of course, we know is H2SO4, to make a better electrophile. E plus is electrophile, right? Because this carbon right here, this carbonyl carbon, is already delta plus, so partially positive, but now when this becomes positive as well, so it'll become positively charged, it makes it even more electrophilic because it wants to quench that positive charge in subsequent steps. Okay? So we have our arrows, again, reversible, and we get to this point right here, right? This OH has not participated in chemistry yet, and this has an H on it, so it makes it positively charged because we have 3 bonds to oxygen. And we have an HSO4 minus counter ion in solution. Okay, so make sure you balance your charges all the time. And we're ready for our next step. So the next step is the alcohol. So our first equivalent of the alcohol is going to act as a nucleophile and attacks the electrophilic carbon. Okay? And so we know what's next. So here's our ROH. So I'm going to keep it generic, this one. Okay. So, oops. So these lone pair electrons are going to act as the nucleophile, and we're going to open up this double bond O and quench that positive charge. Don't forget your arrows. Then, as we know, in the next step, so in the next step, here's what we have. Here's our methyl group, that was right here. Then we opened up this, we moved these double bond electrons up to the OH, so now this is neutral. Okay. We also have this OH down here, which we didn't touch, and we have our nucleophile, which is O attached to an H and an R group. And this is what charges this. It's positive because there's 3 things bonded to this oxygen. Cool. So the next thing we need to do is we got to get rid of this H, right? Because this is not the leaving group that we want. We just added it, right, with nucleophilic attack. We don't want to get rid of this OR group. So what are we going to do? You need some kind of base to grab that. So again, you could probably use any generic base, but in this case, you can also use just, because you're going to be transferring this proton to another part of this molecule, but we don't do intramolecular in this case. So you can just get another equivalent of your alcohol. So here it is, second equivalent of that alcohol. Let me write that. Okay, so second ROH deprotonates the nucleophile, I guess, that you just used in that step. Okay, so here's what's going to happen. These electrons will grab that H, donate to O, right? So in the next frame, got, so the same structure. We didn't touch that OH. We've also got this OH here, which we also didn't touch, and then we have OR, which is